Hello everybody, myself Prasant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our electric machine 2 class, in our last discussions we have talked about the construction and types of induction machines. Today we'll discuss about the torque slip characteristics of induction motor. Before going to the torque slip characteristics, we must have to know some basic things before discussing this torque slip characteristics. And we'll start with frequency of rotor, rotor EMF, rotor current and power factor, and definitely its related problems. Now, as you know that the air gap magnetic field, which is being created by the three-phase winding, distributed winding in the stator of induction motor, and where three-phase balanced supply is being provided, then air gap MMF, which is rotating in nature, and this air gap MMF is rotate at the synchronous speed. And if we think rotor is stationary, in that case the relative speed between the rotor and rotor winding and rotating magnetic field is given as synchronous speed, that is ns. And if we know this ns equal to 120 f by p, that means f, the frequency of the supply, and this is the frequency of the rotor MMF, will be how much? It is p ns by 120. Now when the rotor speeds up, if suppose the rotor speed is n, capital N, then the relative speed of rotor is how much? It is the difference between the synchronous speed and that is the speed of the magnetic field and the rotor speed, that is ns minus n. So rotor frequency, as we got from this one, this is the frequency of the magnetic field. So then the rotor frequency will be p into ns minus n by 120. Now one more important thing you have to know, the difference of this speed, that is the slip speed, is ns minus the rotor speed n. And whenever we represent this difference of speed with respect to the synchronous speed, that is ns minus n by ns, is known as the slip. And so we can write this ns minus n is the slip time the synchronous speed, that means slip time the 120 f by p, that is the synchronous speed. So we can write this rotor frequency p equal to p ns minus n divided by 120. So we can write it p by 120 into, since this is slip, ns minus so this is s by 120 f by p, that is sf. So we can write the rotor frequency is the slip time the supply frequency, and this slip frequency, it is also called the slip frequency, so that is fr equal to s into f. Okay, so this is very important one, that is what is the rotor frequency with respect to the supply frequency or with respect to the rotating magnetic field frequency. So that is equal to s into f. S is the slip. Now come to the case of rotor EMF. Rotor under standstill condition, when rotor is not rotating, so at that time so rotor speed is 0, so slip will be ns by ns, that is equal to 1. So this relative speed is maximum and maximum EMF induced in the rotor in that case. So if this induced EMF is E2, this subscript to denote the rotor. If we denote stator as 1, that is E1, so that is the stator EMF, induced EMF. And in that case, E2 is the rotor induced EMF under standstill condition. Now, when motor speed increases, that is in the running conditions, so relative speed increases, then induced EMF in the rotor decreases. So as a result, we can say E2R, E suffix 2R. So is a rotor induced EMF under running conditions. So E2 is directly then proportional to with NS, and E2R is directly proportional to the NS minus N, the rotor speed. So E2R by E2, what we are getting? This is NS minus N by NS. So this is nothing but slip. So at running condition, rotor induced EMF will be the slip time, the rotor induced EMF at standstill conditions. So this is the rotor induced EMF at running condition. So E2R equal to S E2. Now then rotor current and power factor. So if we call the R2 the rotor resistance per phase under standstill condition, and X2 is the rotor reactance per phase under standstill conditions, then we know reactance X2 equal to twice phi F L2, where L2 is the inductance per phase of the rotor. Now therefore what is this? This is the impedance, that is equal to R at standstill condition, that is root over R2 square plus X2 square. So rotor current at standstill condition, what will be how much? It will be E2 by Z2. Okay, and then power factor, if it is cos phi 2, then it will be R2 by Z2. If we consider the impedance triangle, we will get the say power factor cos phi 2 will be R2 by Z2. Now in running condition, you know this I have shown you in the earlier studying our discussion, that the rotor frequency will be slip time, the supply frequency or stator frequency or magnetic field frequency, not stator frequency, stator magnetic supply frequency or rotor magnetic field, air gap rotating magnetic field frequency. Then E2R, that is that running condition, the rotor induced EMF will be how much? It will be S into E2 that we have seen. So therefore X2R equal to how much? It will be S into X2. So that is this will be twice pi FR and L2. So rotor impedance per phase at running condition, if it is denoted as Z2R, so it will be how much? Root over of R2 square plus S square X2 square. So rotor current at running condition I2R will be AC2 by Z2R. So it will be AC2 by Z2R means root over of R2 square plus ASX2 whole square. So that is S square X2 square. So and power factor at running condition cos phi 2R will be R2 by Z2R. So this will be R2 by root over of R2 square plus S square X2 square. Okay, so this is the rotor current and power factor at standstill as well as this is running conditions. Now with these discussions we will discuss some problem that will clear our idea much better. Let's say this problem 1. Problem is given as a 3-phase induction motor is supplied at 50 Hz and is wound for 4 poles. Calculate synchronous speed, speed when the slip is 3%, frequency of the rotor EMF when it stands at 1200 RPM. So what are the given data? So data is given F equal to 50, P equal to 4. So synchronous speed is equal to n is equal to 120 F by P. So if you put here, so you will get synchronous speed, that is 120 into 50 by 4 you will get, and ns rotor speed equal to ns into 1 minus s rpm. So you know the rotor speed is given, it is how much, 1200. Sleep is for 3%, that is 0.03, and so if you put all this data here, so you will get, so answer will, you will get like this. Synchronous speed will be 1500 rpm, rotor speed when sleep is 3%, so you put s equal to 0.03, and in that case you will get this is from in this equation, so you will get speed when sleep is 3%, and frequency of the rotor when it is 1200. So frequency here, put this, you will get the frequency. Okay, from this you will find out the sleep, then you will get 1200 rpm, so you will get the answer. So the rotor frequency will be 10 Hz. Now takes another problem, that is of the frequency of EMF in the stator of a 4-pole 3-phase induction motor is 50 Hz, and that in the rotor is 1.5 Hz. So you have to find out the slip and speed of the motor. So you know that this is the equation of the synchronous speed, n is equal to 120 F by P, and this is the slip relation between rotor frequency with the supply frequency or magnetic field frequency, then speed of the motor n equal to ns minus 1 minus s. So all data are given, so if you put one after another, then you will get the answers like this. Okay, so this is second problem. Another problem we can see, what is this? So this problem is a 4-pole 3-phase 50 Hz induction motor. Ratio of stator to rotor turns is 3. On a certain load, its speed is observed to be 1450 rpm when connected to 415 volt supply. Calculate frequency of the rotor EMF in running condition, that is FR. Magnitude of the induced EMF in the rotor at standstill condition, E2 phase. Magnitude of the induced EMF in the rotor under running condition, E2R. Assume star connected stator. So what are the data given? P equal to 4, F equal to 50 Hz, supply line voltage is 415 volt, stator side line voltage, rotor turns ratio to stator turns ratio is given as 1/3, so it is 0.333, rotor speed is 1450. Now again apply this equation, n is equal to 120 F by P, sleep equal to ns minus n by ns into 100%, and Fr equal to Sf. And here it is given K E2 phase by E1 phase, and a rotor induced EMF per phase by stator induced EMF per side phase voltage equal to rotor turns by stator turns. So we have studied in the earlier semester class, that is V1 by V2 equal to N1 by A2. There in case of transformer like this. So so E phase equal to E line voltage by root 3. So this will be like this. So now it will be easier for you to get the data and put wherever it is required, and you will get the answer. Say rotor frequency equal to 1.66 Hz. Say per phase rotor voltage is 79.78 volt, and rotor induced EMF at running condition equal to 2.63 volt. So these are the problems, and these are the how you will solve. So everything, hints and keys given. It's just it's the homework. You will try your at your own, and you will definitely solve the problems, and it will clear your understanding also. So we'll come to another problem. This is like this: 4-pole 3-phase 50 Hz induction motor has a star connected rotor. The rotor has a resistance of 0.1 ohm per phase and standstill reactance of 2 ohm per phase. The induced EMF between the slip rings is 100 volt. If full load speed is 1460 rpm, you have to find out slip, rotor frequency, rotor current, power factor on full load condition, and assume slip rings are shorted. So this is the problem given. You have given a 4 pole, that is P equal to 4, supply frequency F equal to 50 Hz, and rotor resistance per phase is 0.1 ohm, and reactance per phase at standstill condition X2 is 2 ohm, and rotor induced EMF between slip ring is 100 volt, and speed is given 1460 rpm. So once again, you know the synchronous speed ns equal to 120 f by p. So f is given, p is given, you can find out the synchronous speed, and slip ns minus n by ns into 100 so percent. So ns you have found, n is 1460, then you can get the slip. Then rotor frequency equal to s into f, s as you have found, and supply frequency is given, so rotor frequency you will get, and rotor induced current, rotor current at running condition I2R will be equal to s E2 by root of say R2 square plus sx2 whole square. So R2 is given, E2 is given, S you have found, X2 is also given, so you can jolly well get I2R, and cos phi 2R, this is the power factor, so will be R2 by root over of R2 square plus S square X2 square. So everything you have found, so you will get the power factor, and your answer will be like this. So slip is 2.66%, frequency of the rotor 1.33 Hz, rotor current will be at running condition 13.15 ampere, and power factor will be 0.887 lagging. So just you will work out this problem at your own as a home task. Now coming to another problem. Here it is given problem 5, 8 pole 3-phase induction motor is supplied from 50 Hz AC supply. On full load, the frequency of induced EMF in rotor is 2 Hz. Find the full load slip and the corresponding speed, rotor speed of course. So what you have given, P is given, F is given, FR is given, full load slip you have to find out, and speed you have to find out. Since you know this relation, S equal to FR equal to S into F, so S equal to FR by F. So FR is given, F is given, so you can find it out. And synchronous speed equal to 120 F by P. F is given, number of pole P is given, so synchronous speed will be found, and the rotor speed N equal to Ns into 1 minus S. So Ns you have found, a slip you have found, so N you will usually will get from this equation. So N equal to 720 rpm. So this is another problem, that is problem 6. A 3-phase 6-pole 50 Hz induction motor has a slip of 1% at no load and 3% at full load. So find out synchronous speed Ns, no load speed NL, full load speed NFL, frequency of rotor current at standstill FRS, and frequency of rotor current at full load FRFL. So you have given P, you have given F, slip at no load is 1% is given, or 0.01, slip at full load 3%, that is 0.03, and slip at standstill, you know, that is equal to 1. So synchronous speed you will find out from the here. No load speed will be this no load slip that is 0.01. So if you put the equation values here, so you will get the no load speed, that will be 990 rpm. And full load speed ns equal to 1 minus sfl. At full load slip is given, you know. So if you put, so you will get full load speed will be like this, 970 rpm. And standstill, of course, the rotor standstill frequency, of course, so rotor is standstill means rotor speed equal to 0. So at standstill is equal to ns by ns, that is equal to 1. So in rotor speed will be f equal to s into f, that is 1 into 50, that is equal to 50 hertz. So at full load, so it will be like this. The full load slip is given. So put here 0.03 into 50, so that will give you 1.5 hertz. Okay, so it's very simple mathematics. Just go through the different relationships and put the values given. You will, or put the value you found from the given data, so you will get the answers. Now another problem is that is it is problem 7. If the EMF in the starter winding of a 6-pole induction motor has a frequency of 50 cycles and EMF in the rotor has a frequency of 2 cycles per second, find the speed at which the motor is running and percentage slip. So data you will found given P equal to 6, if supply frequency is 50 hertz, rotor frequency 2 hertz, 2 cycles per second. So go to the relationship and you will get the answers. That is S equal to at percentage slip equal to 4%, and synchronous speed and rotor speed will be found. Okay, like this. So now we'll come to another problem. A 3-phase induction motor is owned for 4 poles and is supplied for a 50 hertz supply. Calculate the synchronous speed, the speed of the motor when the slip is 3% and the rotor frequency. So given data is P equal to 4, supply frequency F equal to 50 hertz, slip is 0.03. Then rotor frequency will find out the Fr equal to S into F, that is 0.03 into 50. So you will get the rotor frequency, and synchronous speed you will get from here, this one, and the rotor speed from there. So these are the answers. If we talk about another problem, so this is like this. The induced EMF between the slip ring terminals of a 3-phase induction motor when the rotor is standstill is 100 volt. The rotor winding is star connected and has resistance and standstill reactance is 0.05 ohms and 0.1 ohms per phase respectively. Calculate the voltage and rotor current at 4% slips and 2% and 2 is 100% slip, that is standstill conditions. So data given is like this: R2 0.05 ohms, X2 0.1 ohms. So go to this relationship. Per phase rotor induced voltage is equal to E2L by root 3, that is the line. This is the rotor line voltage. So 100 by root 3, that is 57.7 volt. And E2R equal to ASE2. So and Z2 are equal to this, so I2 are equal to this, so Z2 equal to this, so rotor current equal to E2 by Z2. So you go through this relationship and put given data and data you have found, so you will get the answers like this. Okay, so take it as a homework. Okay, now then come to another problem. This is like this. A three-phase 50 Hz induction motor runs almost at 960 RPM on full load when supplied with three-phase supply. So calculate the following: number of poles, full load slip, frequency of rotor EMF, speed of the motor at 8% slip. So data given: supply frequency 50 Hz, rotor speed how much? 960 RPM. So find out the NS synchronous speed 128 by P. So you will get P is given? No, P is not given. So you can count of these equations. Okay. So pole is this. So this is there. From this equation you will find this equal to 6. Slip equal to 0.04, that is 4%. Rotor frequency is 2 Hz and rotor speed at 8% slip will be 920 RPM. So another problem, we'll see what is happening here. So this is like this. 1100 volt 50 Hz delta connected induction motor has a star connected slip ring rotor with a phase transformation ratio of 3.8. The rotor resistance and standstill leakage reactance are 0.012 ohms and 0.25 ohms per phase respectively. Neglecting stator impedance and magnetizing current, determined rotor current at start with slip ring sorted, the rotor power factor at start with slip ring sorted, the rotor current at 4% slip with slip ring sorted, the rotor power factor at 4% slip with slip ring sorted. So this has been given to twice. Rotor current and rotor power factor. The external rotor resistance per phase required to obtain as a starting current of 100 ampere in the stator supply lines. So supply voltage per phase delta connection. So it will be like this. If it is a delta connection, so it will be the same. So 1100 volt. Supply frequency is given. Phase transfer K equal to 1 by 3 by 8. 3.8, so it's 0.263. R2 is given, X2 is given. So from this equation you will find the rotor per phase voltage that is equal to say K times the stator per phase voltage. So this will be like this. So I2 equal to E2 by Z2, you know. So you will and cos phi 2 equal to R2 by Z2. I2 are equal to this. Okay. These equations are given. So first way is this transformation ratio K equal to I1 dash by I2 dash. So 100 by I2 dash. So you will find out. So Z2 dash equal to this and this. So external resistance required R equal to R2 minus R2 dash. So if you put the values given and the values you have found, so you will get the answer like this. Okay. So quickly we will discuss another 2-3 problems. That is, three-phase 4-pole induction motor operates from a supply whose frequency is 50 Hz. Calculate the frequency of rotor current at standstill and the speed at which the magnetic field of the stator is rotating. Given data P4 F 50 Hz standstill condition is equal to 1. So from this equation we will get the answer like this. Okay. Now another problem. This is like this. This is a 4-pole 3-phase squirrel cage induction motor operates at a supply frequency of 50 Hz at a speed of 1440 RPM. At full load, find the frequency of the EMF induced of the rotor. So data given, and you know this is the relationship, and you will get the answers like this. And another quick problem we'll discuss. That is a 3-phase 50 Hz 4-pole induction motor has a slip of 4%. Calculate the speed of the motor, the frequency of the rotor. If the motor has a resistance of 1 ohm at standstill and standstill reactance is 4 ohm, calculate power factor at standstill and the speed of 1400. So data given, you found this, and from these relations you will get the answers. So this is the relation between rotor frequency and supply frequency. This is the rotor power factor, this is slip, and this is rotor power factor at running conditions. So from this you will get the answers. So with this you will get the basic idea of this